Estimate the maximum error in this function at the point 2, 3 if maximum errors plus or minus 0.01 and plus or minus 0.02 are made in x and y respectively. So we want the error in the function f if we change x and y by small amounts, delta x and delta y. Well, the change in f is given approximately by this expression here, as we know. So delta x is the small change in x. Delta y is the small change in y. So if we small changes delta x and delta y in x and y respectively, then an approximation to the corresponding change in f, delta f, is given by this here. So we have to calculate both of these partial derivatives at the point 2, 3. So we want the change in f at the point 2, 3. So the change in f is the value of the function at the point 2, 3 minus the value of the function at the point 2 plus delta x, comma 2 plus delta y. Or we could have this the other way around. I could have f of 2 plus delta x, comma 2 plus delta y minus this quantity. But we can just consider the magnitude of delta f. So it doesn't matter about the order of the subtraction here. So we change the point with coordinates 2, 3 by delta x in the x direction and delta y in the y direction. Delta x or delta y could be positive. But for this question, delta x can have a range of values. It can run from minus 0.01 up to plus 0.01, and similarly delta y can run from minus 0.02 up to plus 0.02. So depending on what values we choose for delta x and delta y from these ranges, we are going to get different values for delta f. So we are going to be interested in maximizing delta f. That'll give us the maximum error in the function. So what values do we need to plug in for delta x and delta y? Let's consider the magnitude of this expression. Now I won't bother writing in where we're taking the partial derivatives. We know that we're taking them at the point 2, 3, so that's assumed, so I won't write that in again. Now we have the magnitude of a sum of two quantities here, and you may know that the magnitude of a sum of two quantities is less than or equal to the sum of the magnitudes. So the maximum value that this quantity can have is actually magnitude A plus magnitude B. So this would be the maximum possible value that this can have. So what's the maximum possible value that the magnitude of the change in f can have? Well, we just split this up. We have the sum of two quantities. The magnitude of the sum is the sum of the magnitudes. Also here we have a product of two quantities. Now it's also a fact, and it's quite easy to prove this one, that the magnitude of the product of two quantities is equal to the product of the magnitudes. This one's easy to prove. This one up here is a bit more difficult. So now what we can do is we can equate this to the magnitude of df dx times the magnitude of delta x, and this is just the magnitude of df dy times the magnitude of delta y. So we can see that the maximum possible value that delta f can have is given by this quantity here. Delta f is less than or equal to this, so it can never be more than this. Sometimes it can equal this, and it's when it's equal to this that it has its maximum value. I mean the maximum value of the magnitude of delta f. So when it says the maximum error here, we're talking about the magnitude of the maximum error. So we're going to get some positive quantity for this, and that's okay. Of course, delta f could be negative. We could talk about the minimum value of delta f or the maximum negative value, if you like, but we'll just take magnitudes. So as we saw before, delta x goes from minus 0.01 to plus 0.01. So the maximum value that this can have is obviously 0.01. It's obviously not negative. It has to be positive, getting the magnitude. And it's, as you know, it can be any number up to and including 0.01. So obviously we plug 0.01 in for this, and similarly for delta y, it runs from minus 0.02 all the way up to plus 0.02. So we plug plus 0.02 in for this in order to maximize this expression. Now what about the derivatives? Well, they're straightforward. Let's start with df dx. Differentiate x squared with respect to x, we get 2x. Y squared goes to 0. We treat y as a constant, so we have constant times y here, so when you differentiate with respect to x here, we get that constant y. And we want to work this out at the point with coordinates 2, 3. So we have to plug 2 in for x and 3 in for y. So we have 2 times 2 is 4 plus 3 is 7. Next we need df dy. So differentiate x squared with respect to y, that goes to 0. This gives us 2y. We're holding x constant here. Differentiate this with respect to y. We get that constant x. And we want to work out this expression at 2, 3. So we have to plug 3 in for y and 2 in for x. So we get 6 plus 2 is 8. So calculating this, we get 0.07 plus 0.16, so that's 0.23. So this is the maximum change in f, is the magnitude of the maximum change in f, I should say, is 0.23. That's given that we have the maximum values for the change in x and the change in y here. Well, the maximum values for the magnitudes of these quantities. Let's look at the value of the function at the 0.23. So we have 2 squared is 4 plus 3 squared is 9. That's 13 plus 6, that's 19. So by varying delta x by these amounts here, we will vary the value of the function at 2,3, that is 19, by this amount. Now this is the magnitude of the maximum change in f. So, you know, we'll be varying 19 by plus or minus 0.23. We can try to visualize what's going on by looking at the point with coordinates 2, 3 and considering a rectangle surrounding that point. One side of the rectangle is twice the maximum magnitude of delta y, which is 0.02. So we multiply that by 2 obviously, and we get 0.04. So this runs from 3 minus 0.02 up to 3 plus 0.02. So from 2.98 up to 3.02. And the change in x runs from minus 0.01 up to plus 0.01. So if we get 2 minus 0.01, we get 1.99 for this point here. This point here is just corresponds to this point, which is 2, and this point here is 2 plus 0.01, which is 2.01. So x runs from 1.99 up to 2.01 for this point here, and y runs from 2.98 up to 3.02. So we can imagine calculating f for all values in this rectangle. We know that at the point 2, 3, the value of the function is 19. It appears that the function has its maximum value in this region at this corner here. So when this quantity is plus 0.01 and when delta y is plus 0.02. Now both derivatives are positive, so we don't even have to worry about the magnitudes of them. So this value is a possible value for delta f. So the largest delta f occurs at this point here. So the maximum value of the function in this region must be at this point, because delta f is the difference in these two values. And this value here is 19 plus 0.23. So this value is 19.23. Now it's possible that delta f can never attain this the value of this expression here, because one of these derivatives could be negative and the other one could be positive. So by taking magnitudes, we tend to add the two together, but when they should really kind of cancel each other out. So you need to watch for that. But still, we can work with this, and it might give a value that's not possible for delta f, but it does give a value that is possible here, only because both derivatives have the same sign. The minimum value for delta f is 19 minus 0.23, and if you think about it, it must correspond to this point here. If we remove the absolute values, the magnitude lines, and make this negative and this negative here, well, we are going to get minus 0.23. So that would give us 18.77 for this point.